Okay, so let's continue our discussion on group theory. Yeah, so in the last lecture, I guess we had introduced the concept of Langrange's theorem, right? Langrange's theorem, and the simple statement was that if you consider a subgroup of G, then the order of that subgroup will divide the order of G, provided G is a finite group. Okay, and it had two important consequences. We had discussed about these in the previous lecture. So before viewing this lecture, I'll recommend the previous lecture to have a better understanding. Okay. So let's discuss an example regarding normal subgroups, which will have an obvious which will give an obvious application of Lagrange's theorem on how does it simply work. Okay. So the example is in this way that we consider the subgroup generated by the permutation 1, 2, 3 in S3. Okay. So I hope you guys know what this cycle notation means. So this represents the function which sends 1 to 2, 2 to 3, and 3 back to 1. Clear? Okay. Now, so we want to check whether H is a normal subgroup of S3 or not. Okay, that's our goal. Now if you recall the equivalent statements regarding normal subgroups, there was an important statement which said that the normalizer of H is equals to the whole of G. This would imply that H is a normal subgroup of G, and we would rather proceed with this. We'll try to show this very statement in order to show that H is a normal subgroup of S3, because this will indeed give a nice result using Lagrange's theorem. Because observe, by definition, H will be obviously a subgroup of the normalizer of H in G, right? So then by Lagrange's theorem, the order of H must divide the order of the normalizer of H. Now the order of H will obviously be the order of this cycle, because we know that in case of a cyclic group, the order of the element which generates the subgroup or the group will be equal to the order of that very subgroup or group, right? So order of H will be 3, because this permutation or this element of S3 will will have order 3, right? So 3, that means 3 must divide the normalizer of H in G, right? But observe one more thing. By definition, the normalizer of H in G is a normal subgroup of G. Sorry, I mean it's a subgroup of G. In this case, it's just a subgroup of G. But then that implies that the order of this normalizer must divide the order of G, right? But the order of G is 6, because the order of S3 is 6. Then what are the only possibilities for the order of the normalizer of H in G? 3 must divide this, and this must divide 6. Therefore, observe that the only possibility for the normalizer of H in G is 3 or 6, right? Now, if it equals 3, then the normalizer of H in G must equal H. That is, if normalizer, or I should say it like this, if this happens, and if this happens, then the normalizer of H in G must equal G. So we just have to check the possibility of one of these two conditions, because both can't occur simultaneously, right? So if I consider this case, or I want to verify this case, then there's a very very trivial observation that this cycle 1, 2, this is not in H, but this is in the normalizer. You can justify this on your own, you can verify this, but it's a very very obvious verification. If you just remember what by definition normalizer of a set in G is, then you will surely be able to understand the logic behind this. Okay. Clear. So that means the normalizer of H in G cannot equal H, Therefore, this can't happen. So the only possibility is this, that the normalizer of H in G is G, but this would imply H is normal in G. Right? Got it? Now, normal subgroups do not behave as well as a subgroup. Okay, subgroups are very well behaved. The most obedient students of the subject group theory. Normal subgroups are not that obedient students. Because there's a very obvious observation, like we have discussed this previously also, that the relation of being subgroup is transitive in nature, right? That is, if n is a subgroup of M and M is a subgroup of G, then n is a subgroup of G. Okay, but this does not happen in case of normal subgroups. The relation of being normal subgroup is not transitive. Okay, wait a sec. Okay, now if I talk about an example, then you can justify this yourself, that the subgroup generated by S is normal in the subgroup generated by S and R square, and this is indeed normal in D8. So so if you quickly recall D8, then it consists of the elements R and S, right? Which obeys the condition that R cubed must be 1, S squared must be 1, and RS must equal RS inverse. And geometrically, the element R represents a single rotation from vertex to vertex anti-clockwise. You might think of it like that. And S gives a single reflection. Okay, so a single rotation from vertex to vertex, maintaining symmetry obviously, a single reflection and combinations of rotations and reflections maintaining symmetry. This constitutes the group D8 for a four-sided regular polygon. You can obviously extend this to any n-sided regular polygon. Then the elements will be their rotation and reflections maintaining symmetry, and the combinations of rotations and reflections maintaining symmetry. Okay, so this is obvious. You can justify this, and you can further also justify the fact that S is not normal in D8. And the reason why S is not normal in D8, see, if we can establish commutativity or the conjugates being invariant for the generator, then it must abide by it must be abided by the whole group. That is, if I can show that there exists some element in D8 such that XS X inverse is not in this, then it's trivial that any element of this set will not abide by the definition of a of the conjugate being still in the same group. That is, S will not be normal. Okay, that's what I'm trying to say. Like if you recall the definition of being normal, we said that H is normal in G if for every element in G, say small g, GH must be equal to HG. But that means that GH1 is equals to H2G, and H1 and H2 need not be same. So the other way of saying is that GH1 G inverse must still be in H. Okay, for every element H1 in H and G in G. That's precisely what I wanted to say. So suppose if H is a normal H is a cyclic subgroup, and you consider this statement for the generator of the cyclic group, then this statement should also obey what is happening for the generator, will also obey for the whole, every element of the group, because every element is just some combination of the generator. Observe that this condition holds for X is equals to R, because R S R inverse is, I guess it's SR squared, but this cannot be in S, right? I guess it's clear. Therefore, this is not happening. So normal subgroups do not obey the transitive property. One more important observation regarding normal subgroups, this is also quite an important observation which relates to the concept of index. Let me write as a proposition. Any subgroup of index 2 is normal. Okay. If you quickly recall what index by definition was, so it was basically the number of distinct left cosets of that very subgroup. And we used to usually denote this as G, like this. This gave the index of H in G, or other way of saying it gives the number of distinct left cosets of H in G. Okay. So any subgroup of index 2 is normal. How do we prove this? Proof is fairly simple. If I consider a subgroup H of G such that the index of H in G is 2, that means there exists precisely two distinct subgroups of two distinct left cosets of H in G. Say, one will obviously be the identity left coset, that is 1H or just H, and one will be GH for some small g in capital G, right? Every other left coset of H in G represented by any non-identity element of H will represent the same left coset GH. Do view the lectures on quotient groups and cosets, then you will get a better understanding of what do I mean by the concept of representatives. So if now we know that cosets partition the group, right? Therefore G is a disjoint union of H and GH. So suppose if this is G, then it's a disjoint union of H and GH. But then observe, GH is nothing but G minus H. Sorry, G minus H. That is the complement of H in G. But I can do the same for right cosets as well, right? Because we know that the number of distinct left cosets equal the number of distinct right cosets, right? So in a way, the index represents the number of distinct left as well as the number of distinct right cosets. So so it will also have precisely two distinct right cosets, say H1, which will again precisely be H, and some HA, where A is a non-identity element of G, of G. So I should mention it is a non-identity element. But again, what I said, since you have only two distinct right cosets, so the right coset represented by any non-identity element of G will obviously represent this coset as well. And since the G we are talking about here, it's a non-identity element of capital G, so HG must equal HA. So talking about HA is equivalently talking about H. But then again, we get the by the same concept, because right cosets also partition G, we will get the same observation that G is a disjoint union of H and HG. But that would mean HG is the complement of H in G, but this is exactly GH, right? And since this small g was an arbitrary non-identity element of capital G, this precisely means that H is normal G, right? This precisely means that H is normal G, right? Okay. Now we have studied what the Langrange's theorem says. Now whenever we talk about some theorem which is a one-sided implication, an obvious question should arise that whether the converse of the statement is true as well or not, right? We said that if H is a subgroup of G, then the order of H must divide the order of G. But my question is that is the converse true? That is, if G is a group of say order n, then whether there exist subgroups of G with orders equal to factors of G. Other way of saying this, suppose if order of G is say 6, then does there exist a subgroup of order 2, a subgroup of order 3 as well? That is, every factor of 6 corresponds to the order of some subgroup of G or not. Like we know if there exists a subgroup, then the order of that subgroup must be a factor of the order of G. But is the converse true? So the converse is precisely not true in general. This is not true in general. It is true in some specific cases, but it's not true in general. An example of this is, let's say, if you consider the collection of all symmetries of a regular tetrahedron, consider the collection of symmetries of a regular tetrahedron. Say we represent this by G, say G. Now, obviously, we are talking about symmetries, right? So if we are talking about symmetries, then this necessarily forms a group. As a subgroup of the symmetric group, you might think of it about. My claim is that this group has order equal to 12. Try and verify this out. A tetrahedron is sort of a polygon of this form. Yeah, it's sort of a three-dimensional triangle. Okay. Verify this out, that the collection of all symmetries of a regular tetrahedron comprises only 12 elements. That is, there are exactly 12 distinct symmetries of a regular tetrahedron. Okay. My claim is that yeah, okay, let's go step by step. So order of G is 12. Let H be a subgroup of G such that the order of H is 6. Now 6 is clearly a factor of 12, right? But if order of H is 6, then that precisely means that the index of H in G, which is by Langrange's theorem, mod of G by mod of H, or order of G by order of H, but that must be 2. So this readily implies that H must be a normal subgroup of G. So it is a normal subgroup of G, and if H is a normal subgroup of G, then we can define the quotient group. The quotient group precisely has 2 elements, so it is isomorphic to Z2. Isomorphism means that the group structures are equivalent. Any group of order 2 is isomorphic to Z2, because any group of order 2 is somewhat a cyclic group, right? So any group of order 2 is of sort like this, right? So it's a cyclic group generated by A, where the order of A is 2. So any cyclic group of order n is isomorphic to Zn, hence it's isomorphic to Z2. That's quite a trivial, case. Okay. Yeah. So this is what we have now. Now, for every element in G, Gh squared by the operation on a quotient group is G squared H, right? Is G squared H. So what can we say is that it's precisely 1H, right? So that means G square must be in H, right? Right? Is it clear? Okay. Okay. So yeah, suppose this happens. This comes from this comes readily from the property of the symmetries of a regular tetrahedron. Okay. Now, if G square is in H, what more can we say? Okay, let it be for this moment. Now, suppose G is an element of A such that the order of G is 3. Okay. But if order of G is 3, then G equals G squared whole squared. But that's precisely, because this is g squared whole square is g cubed dot g cubed is 1 because order of g is 3, so it's, I guess it's clear. But this is the square of g square. Now g square is in H, so its square will also be in H, so this must be an element of H, right? So in other words, H contains all elements of order 3, right? But if you carefully observe the collection of all symmetries of a regular tetrahedron, there are exactly 8 distinct elements of order 3. 8 distinct elements of order 3. But the observation we get here is saying that H contains all elements of order 3. That means every element of order 3 must be in H, but H consists of only 6 elements. Therefore, this is a contradiction, right? That means there is no subgroup of order 6 in G. Okay. Therefore, the converse is not readily true, right? But it's true in some cases. It's true in some cases. For example, if I talk about a finite group, so this is called the I guess it's called the Cauchy theorem. It's called the Cauchy theorem for finite groups. So this theorem says that if G is a finite group, and P is a prime dividing the order of G, dividing the order of G, then G precisely has an element of order P. Then G has an element of order P. We are not going to prove this statement right now. When we will be discussing Silo theorems, after that we will give a very elegant proof of this. At that point, this proof will be quite easy. Okay. So if G is a finite group and P is a prime dividing the order of G, then G has an element of order P. This is one important theorem which is slightly related to the converse of Langrange's theorem. And one more is what I even just now talked about. What it is the Silo theorem. The Silo theorem says that if G is a finite group of order P to the power alpha m, where alpha is a positive integer, P is a prime not dividing m, P is a prime not dividing m, then G has a subgroup of order P to the power alpha. Okay. These sort of subgroups are also called Silo P subgroups. We will discuss them in some future lecture, and we will obviously, 100% we are going to have a dedicated lecture to Silo theorems because that's quite an important aspect of proof theory. Okay. Okay, so we have discussed a lot about these things. Now let us move on to construct a new form of a group, which can be constructed using some given subgroups of a group. Okay, so it's often called the product group. It might also have some other related terms, but I'll prefer calling it the product group. But what it basically says is that let G be a group, and let H and K be subgroups of G. Define a set. I'm not speaking of a group. I'm defining a set. The set HK, which is defined as the collection of elements of the form small h small k. Obviously, we are imposing the operation, which is the operation of the group G, such that H is an element of capital H and K is an element of capital K. Okay. Clear? Okay. So this is a set. Now, why are we doing this? So, like it's a very obvious, what can I say about this? It's a very obvious nature for, obvious nature to do things, to extend things with the tools which we already have, right? Like we always try to classify examples with the examples we already have. If we have something, we always want to extend it to, various other things. We know the concept of a group, we know the concept of a subgroup. Using the concept of one or more subgroups, we are trying to extend it to form new forms of groups. That is the goal behind this. Like, as we consider a normal subgroup, we extend our concept to the concept of quotient group, which forms an elegant classification of groups, right? So this is one more, sort of a constructed group using the tools which we already have. Okay, so this is a set. This is, for now, it's a set. And obviously, it's surely non-empty because one is obviously in HK. Whatever. What can I say about the order of HK? What is the order of HK? That's my question. So now, see, observe that HK can be written as the union of the elements of the form H capital K, where H ranges over the elements in small elements in capital H, right? And precisely these are all the left cosets of K, right? Because we can consider H to be an element of G as well. Now the obvious question arises from here is that if I sum over these elements, then I'll precisely get the, that is if I consider the number of distinct left cosets of K using the elements H, then I'll get the number of elements in capital H capital K. But there's a slight glitch here because their elements might repeat in these form of elements, like two cosets might have the same representative. So we need to omit the elements which repeat, right? Now each coset will have exactly, this comes from Langrange's theorem, each coset has exactly order of K elements. So the only question which we need to answer is what are the number of distinct cosets, and that will precisely come after omitting the number of repeating cosets. How can we do that? Suppose I have two elements. Suppose I have two elements H1 and H2 from capital H, such that H1 capital K is equals to H2 capital K. So these are two cosets which are identically same, structurally same, but this means H1 H2 inverse must be in K. Well, observe that since H1 and H2 are elements from capital H, by closure, H1 H2 inverse must also be an element of capital H. But this means H1 H2 inverse are elements of, one sec. This means H1 H2 inverse are elements of H intersection K. But that implies H1 of H intersection K is same as H2 H intersection K, the cosets of H intersection K, right? Therefore, the number of distinct left cosets of the form small h capital K is the number of distinct left cosets of the form. So this is equivalent to the left cosets, or I shouldn't write here equivalent, I should write it as a statement here. Number of distinct left cosets of the form HK is the, because if I omit these values, then I'll get the number of distinct left cosets of H intersection K as well, is the number of distinct left cosets of H intersection K. But H intersection K is a subgroup of H. H intersection K is a subgroup of H. So the number of distinct left cosets of H intersection K, this precisely should be the order of H divided by the order of H intersection K. And each distinct left coset or each coset will have exactly this number of elements. So this precisely gives the answer that the order of HK is nothing but order of H by order of H intersection K times order of K. Or the other way of writing it as order of H times order of K divided by order of H intersection K. Got it? Now, I want to construct a group out of this set, or I want to consider the condition under which this set might form a group. Okay. The first question arises: is it always a group? Is HK always no, precisely by definition HK must be a subgroup of G, right, by closure property. So is it always a subgroup of G? That is the first question. Okay. So HK is HK a subgroup of G always? So whenever he asks us questions that something happens always, the obvious answer is always no. And the example which abides by my saying no is if you consider G to be S3, you consider S to be the cyclic group generated by the cycle 1, 2, K to be the cyclic group generated by the cycle 2, 3, then observe the only element in the intersection of H and K is 1, right? Is 1. Therefore, the order of HK by definition, I mean from here, must be order of H times order of K by 1. But order of H is 2, order of K is also 2, so it's precisely 4. But order of G is 6. So this does not divide order of G. Right? So therefore, HK cannot be a subgroup of G. Right? It doesn't obey the Langrange's theorem. Got it? So it's obviously not always a subgroup of G, but when is it a subgroup of G? Okay. So when is HK a subgroup of G? Okay, so let me answer this in this way. Suppose it's a subgroup. Suppose HK is a subgroup of G. What are the observations which we can carry out from here? First thing first, see, K is a subgroup of HK by definition. H is also a subgroup of HK by definition. But then by closure, KH is a subgroup of HK by definition, or at least a subset. Let me consider the weaker statement, a subset of HK. Okay. Now suppose I choose an element out from HK. Let small h small k be an element out from HK, but then by closure, the inverse of this, which is precisely of the form K inverse H inverse, is an element of HK. Right? Right. So let A inverse be HK, which is in capital HK. But then A is of the form H1 K1, as the inverse of A inverse must also be in HK, because HK is a subgroup. We have assumed this to be a subgroup. Right? Which implies this is also in HK. But we don't know about H1 and K1 for now. Right? I guess it's clear for now. But observe, so if A is of this form, because A is in HK, then A inverse is precisely of the form K1 inverse H1 inverse. But this must equal the H formation of HK. I shouldn't write it like this. This will make it clearer. See, A inverse HK, which is equals to A inverse, but A inverse from here is equals to K1 inverse H1 inverse. But K1 inverse H1 inverse is an element of KH by definition. So I choose an element HK arbitrarily from capital H capital K, and I show it to be an element of KH. So that precisely means that HK is contained in KH as well. But that means from here and from here, this precisely means that HK must equal KH whenever HK is a subgroup of H, subgroup of G. Okay. This is one fair observation. Now my question is, what happens if this condition is satisfied? Suppose this condition is satisfied, or I shouldn't immediately say that this condition is satisfied. Let me come up like this. I want to check when is HK a subgroup of G. Okay. Suppose I choose an element out of HK. Okay, let A be, let A be in HK, B be in HK. For HK to be a subgroup, we need to show AB inverse is in HK, right? Because I already said that HK is clearly non-empty because one is obviously in HK because one is in H and one is in K. Trivial, right? Because H and K are subgroups. Now, obviously, since A is an element of HK, so A must be some form of H small k. B must be some form of H1K1, clearly because since H is in capital H and K is in capital K, and here H1 is in capital H, K1 is in capital K, right? But then what can I say about AB inverse? So obviously AB inverse is HK times the inverse of H1K1, but that is K1 inverse H1 inverse. Observe that for this to be in HK, sorry, yeah, we need to show its subgroup. Yeah, so for this to be in HK, we need to write it as some H2K2, and that is possible only if these elements these elements can be associated together and can be form of their position can be interchanged, right? And that is possible only if HK is equals to KH. That is what I want to say is that, see, if I group them up, so it's of the form HK K1 inverse H1 inverse. Suppose I take this to be K2, then I get the then I get AB inverse is of the form H K2, and suppose I choose H1 inverse to be H2, HK2 H2. But there is no more possible manipulation here. We need to show that it's in HK. The only possibility is if I can interchange these two positions, right? By interchanging, I do not mean that I want them to commute. I want to say that if I can say that K2 H2 can be written as some H3 K3, where H3 and K3 are from H and K respectively, then observe, then this can be written as HH3 K3. By closure, this is an element of capital H, this is an element of capital K, so AB inverse is an element of HK. And this portion is possible only if this happens, right? Therefore, we have a very nice proposition. Let G be a group and let H and K be subgroups of G. Then HK is a subgroup of G if and only if HK equals KH. Okay, clear? From here we have an immediate corollary. The corollary is also quite obvious. It says that if I choose two subgroups, while one is inside the normalizer of the other, what I'm trying to say is that suppose let H and K be subgroups of G such that H is in the normalizer of K in G. Okay. Then HK is a subgroup of G. Specifically, we can further extend this statement. Specifically, if K is normal in G, then HK is a subgroup of G. Observe that the same proposition can also be written interchanging the positions of H and K, right? So how do we prove this? To prove this, it suffices to show that HK equals to KH. Okay. So how do we do that? Yeah, we try to show this statement. Suppose. Okay. or we rather we try to show hk is equals to kh. Okay. So let h be an element from capital H, small k be an element from capital K. I need to show that hk H inverse is in K, right? So that precisely shows this. Okay. Sorry, I don't need to show this. This happens because H is a subgroup of the normalizer of K in G, right? Then this happens, right? HK H inverse is a subgroup is inside K, right? But then, then what can I say about the element HK? So I can write HK as HK um, H inverse of H, right? Now this is an element in K from here. This is an element in H, so this is an element in HK, right? Sorry, this is an element in KH, right? And this was an arbitrary element in HK, capital HK. So this implies HK is contained in KH. Similarly, how can we write KH? So KH can be written as H times H inverse KH, right? This is an element of capital K. This is an element of H. Therefore, this is an element of HK. This was an arbitrary element of KH. So that implies KH is an element of is a subset of HK. So this statement and this statement precisely means HK must equal KH. Okay. Okay. Clear? Okay. So this condition immediately gives us a very important definition of a set, normalizing a subgroup level. Definition. If K is a subgroup of G, then a subset of G is said to normalize K. If A is contained in the normalizer of K in G. Right? Yeah. Similarly, some subset B of G is said to centralize K if B is contained in the centralizer of K in G. Okay? Clear? So from this definition, it's utterly obvious that HK is a subgroup of G. When does this happen? If H normalizes K. This comes us from the corollary that H normalizes K or K normalizes H. Right? Right. But is the converse true? Again, since this is a one-sided implication, is the converse true? Is the converse true? I ask you people to justify the examples just so that you get deep into the topic. So again, since I am asking this question, is the converse true? The rather kind of obvious answer should be no, and it's indeed no. Right. That is what I'm trying to say as a converse is that if I have two subgroups, or let's say we have a subgroup H and a subgroup K of G, where H normalizes K or K normalizes H, then sorry, I'm sorry, I'm not speaking about this. I'm speaking about this. Suppose HK is a subgroup of G, then will always H normalize K or K normalize G. Yeah, that's what I'm trying to say. K normalize H. That's again not true, because if you consider the group D8 as a subgroup of S4 and you consider K to be the subgroup generated by the 3 cycle 1, 2, 3, then you can justify that HK is a subgroup of G, but neither H normalizes K nor K normalizes H. Okay, clear? You can justify this on your own. Okay, so let this lecture be up till this much. In the next lecture, we will be starting with the concept of isomorphism theorems. Okay, so meet you guys in the next lecture.